We're in 2.7 where we're talking all about these polynomials, their roots, and how we can guess the roots and make predictions about the roots. And all of this is actually from this guy named Rene Descartes. And he has this last kind of rule that we're going to look at here, which is the Descartes rule of signs. And it comes from him noticing something about these polynomials and their different possible roots. So remember, when we're talking about the roots, we're talking about our graph, rough sketch, and some polynomial. And if we're talking about positive roots, that means we're talking about this side, right? So anything that passes on the positive x axis is a positive root, right? Any x-intercepts here. And anything that's passing on the negative x-axis is a negative root. And then we also talked about we have these roots that are imaginary roots where we don't have an x-intercept at all. So what Descartes noticed is he said, so you have this beginning part is just you have a normal polynomial function. He saw that the number of possible positive real roots is equal to the number of changes in sign of the coefficients, or is less than this by an even number. And we'll talk about what that looks like. Then he said the number of possible negative real roots is equal to the number of changes of sign of f of negative x. So how we're going to use this, if you look at example 4, this is a little tricky because we're not really doing much actual math, we're just noticing some patterns here. So our possible positive roots come from if you use f of x just as it is. X to the third is a positive number. 2x is a positive number, and negative 11 is a negative number. So our number of changes in the sign is just one change. So what Descartes said is he said if you have one change in sign, that means that you have the number of possible positive roots is 1. Or if you decrease that by an even number, but in this case 1 minus 2 is negative, so we're not going to count that. So it's just one possible positive root. Then our possible negative root, let me draw a line here, we're going to kind of draw small here too. Possible negative root, now you take f of negative x instead of f of x. So anytime you see an x in the original equation, instead put a parenthesis negative x to the third plus 2 times negative x minus 11. If you took negative x to the third power, that'd still be negative, so you still have a negative x to the third, and that's because this power here is odd. Anytime it's an odd, it won't change the sign. But this positive 2x will now become a negative 2x minus 11. So now if we look at this the same as we did in the positive possible ones, this is a negative, this is a negative, and this is a negative. There are 0 sign changes, which means that our possible negative roots is just 0. Pretty weird pattern that he noticed. Now remember, you can have positive real roots, you can have negative real roots, and then you can also have those imaginary roots. So we have one last kind of situation that we have to think about, and it's those imaginary roots. And the easiest way to do this is to make actually like a table. So if you have your possible roots, you can either have positive real roots, you could have negative real roots, you could have imaginary roots, and then you have your total number of roots. So if we have this table, we know that we can have one possible positive real root, 0 negative roots. The degree of the polynomial was 3, meaning our total has to be 3. So as a reminder, must match degree. So I have one real root, or one positive root. I have 0 negative roots, which means I must have 2 imaginary roots. The other thing to remember is since when we're finding those imaginary roots, remember it's from the quadratic formula and we have that plus or minus. So that's why imaginary roots have to come in pairs. So must come in pairs. So if you're ever filling out this table and you have like a 1 for your imaginary root, that's not possible. So you've done something wrong because it has to be a 2, a 4, 6, 8, so on. So using this table then, we have that our final answer, how you'd put it in Go formative, and this is going to look a little odd. I'm going to have to make sure I go through and double check everybody's answer. But your positive roots, positive, you'll put positive, colon, 1, comma, negative, colon, 0, comma, imaginary, colon, 2. So not a ton of actual like arithmetic happening. We're just kind of looking at patterns. Let's do example B before you ask any questions to see if maybe that'll clear up some questions you might have. Example B is bigger, so it's going to have more possibilities. It's a little more complicated. Alright, so for example B, again, start with your possible positive roots where you don't have to change anything. You just look at each part. So x to the 6th is positive, negative 2x to the 5th is negative, 3x to the 4th is positive, negative 10x to the 3rd is negative, negative 6x squared is negative, negative 8x is negative, and negative 8 is negative. So our total number of sign changes, we have 1 change here, 2 change, 3 change, and then nothing else changes, right? So we have total 3 sign changes, which means that we have our possible positive roots are going to be 3 or 1. And where I got that or 1 is that second part of Descartes' rule of signs there, where he said you can take away a pair. So anytime you have a number that's bigger than 1, what you're going to do is you're going to take this number and you're going to subtract 2 until you get to 0 or 1. You don't want a negative number because it doesn't make sense to say that you have a negative 1 possible positive roots. That just doesn't make any sense. You can have 3 possible positive roots at most, or you have 1 possible positive root. So that's going to be one confusing part here. Let's look at our negative one. So our possible negative roots come from f of negative x. Eventually, you'll probably be able to skip this first step if you're good with understanding when a power is going to stay negative or positive, but for now, we'll fill this out. So negative x to the 6th minus 2 times negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x to the 3rd minus 6 times negative x to the 2nd minus 8 times negative x and minus 8. So anytime you have an even power, what's going to happen is that negative is just going to drop, because if you raise, like, so if you think about negative 1 to the 2nd power, that's positive 1, because negative 1 times negative 1 is 1. Negative 1 to the 4th power would be the same thing. It'll end up positive 1. So this is actually going to stay a positive. This one will stay a negative, but it's going to be a negative negative. This will become a positive. This will become a positive, and then everything else will stay negative. So you can go through and change anything with an even power. Then this will be an x to the 6th. Negative 2 times a negative 1 will be a positive 2, x to the 5th. This will stay a positive 3, x to the 4th. Negative 10 times a negative x will become a positive 10, x to the 3rd. This will stay a negative 6, x to the 2nd. This will become a positive 8x, and then minus 8. So if I'm looking at my signs, x to the 6th is positive, x to the 5th is positive, x to the fourth is positive, x to the third is positive. Negative 6x squared is negative. Let's put negative 6. 8x is positive, and then negative 8 is negative. So the number of changes in sign, there's a change here, there's a change here, and there's a change here. So that's 3 sign changes again. Which means that my possible negative roots is going to be 3 or 1 again, because again you have to just subtract by 2. That's going to be kind of one of the confusing parts to remember. Okay, anytime you have that or, it's really important that you make that table because it's really hard to figure out how many imaginary zeros you'll have without it. So let me draw, this does not want to straighten out. Okay. So our possible zeros, or our possible roots, we'll have a positive column, a negative root column, an imaginary column, and then our total. So if I have 3 positive roots, and then let's say I also have 3 negative roots, I know that I have a total of 6 roots, and that comes from my degree. 3 plus 3 is already 6, so I have 0 imaginary roots. Okay, now let's say instead of, I still have 3 positive roots, but now let's say instead of 3 negative roots, let's say I have 1 negative root. 3 plus 1 is only 4. I need a total of 6. So that means that I have to have 2 imaginary roots. Now let's do the same logic, but instead of 3 positive roots, let's say I have 1 positive root. But then I do have 3 negative roots. That's a total of, I need a total of 6. Again, that's a total of 4, so that means I must have 2 imaginary roots. And then the last possible thing that could happen is that I have 1 positive, 1 negative. That's only a total of 2 roots. I need 6. So that means I have to have 4 imaginary roots. So by building this table, I know that my positive roots, we already had that. So the positive was 3 or 1. The negative was also 3 or 1. But now the imaginary, I can pull from this table. Right? It's this column right here. You don't need to repeat the 2 though, so it would just be 4, 2, 4, 0. All right, do we have any questions at this point?
On B, is that how we put it into the goal formative?
Yes, what I highlighted at the end, that's how you're going to put it in.
Can you go over why we're supposed to subtract 2 from the 3?
So the reason that is, he said it's kind of a throwaway part in this rule. It says it's the number of changes in sign or is less than this by an even number. And that's the part where you're subtracting by 2. The reason that is if you think about, let's just think about a specific example. If you think about x to the third, right? If it says you have 1 possible positive root or 3 possible positive roots, what's happening is this is 1 possible positive root right here, right? But then our other 2 roots have to be imaginary, so that's like where you subtract the 2. Or you have that this does pass through all 3. And that's why you have 3. So you have to take away the 2 because it's either that that you have a total of 3, or it rises above that and your other 2 roots are imaginary. So I guess the reason you have to subtract by 2 is because these imaginary roots have to come in pairs. It is sort of an odd thing, so I guess just kind of remember you have to subtract by 2 until you have 0 or 1. Does that kind of help? I know it's a little weird. Kudos to Descartes for noticing all this stuff. All right, let's do one more example together, and then I will set you free on your homework. So part C, again, to find our possible positive roots, just look at 2x to the 4th is positive, negative 8x to the 3rd is negative, 6x squared is positive, negative 3x is negative, and then this is positive. Lots of sign changes here. So there's 1 change, 2 change, 3 change, 4 possible changes here. So 4 sign changes. So our possible positive roots, at most, we have 4. And I guess, Bella, let me draw it out here while we're doing this. So we have a positive 4, meaning we have something, this is a 4th degree polynomial, roughly drawn. Notice here that there's 4 roots. There's 1, 2, 3, 4 that are positive. Or, let's say that, actually, let me draw this. Okay, so this is our 4 positive. Or, oops, I didn't make it smaller. This thing, I'm just trying to do one thing, here we go. Or this just passes through like this, right? And then we only have a possible root here and here. So that's where I subtracted 2, right? It got shifted up and then we only had 2 real roots. Or it's shifted up even further and there's no real roots. That's just from shifting that graph up or down. And you can just do that with, numbers by subtracting 2 each time. So that's my possible positive roots. For my negative roots, this is the annoying part, you have to do that f of negative x. And like I said, if you're good at doing it in your head, great, kudos. If not, this works just fine. So 2 times negative x to the 4th minus 8 times negative x to the 3rd plus 6 times negative x squared minus 3 times negative x plus 1. This negative x to the 4th will become a positive, and so will the negative x squared. That'll become a positive. The rest will stay. So this will stay as a 2x to the 4th. This will become a positive 8x to the 3rd, because it's a negative negative. This will stay a positive 6x to the 2nd. A negative negative becomes a positive 3x plus 1. So if I look at this, this is a positive, a positive, a positive, a positive, and a positive. Meaning there's 0 sign changes. Which means this graph does not have any x-intercepts that happen on, the negative side. So this never crosses over like this. It's always over here. So my possible negative roots are just 0. Without the table, by shifting this around, yeah.
Okay, so for that, do you multiply the negative x into each of the things, or like how do you?
Yeah, you're doing a substitution here, and basically what's happening is anytime you have an even power, the sign won't change. But if you have an odd power, the sign on the coefficient will change. That's kind of the trick for doing it in your head. So then, my imaginary roots, and you might be able to see just by shifting that W kind of around, but if not, our table can help us. So our possible roots We have positive roots, negative roots, imaginary, and then our total. Try to be neat here. So this was a fourth degree, meaning our total has to be 4. Our first possibility was that there was 4 positive roots. We know that there's 0 negative roots. If we already have our 4 positive, that means there's 0 imaginary. Then we could have 2 positive roots. We know we have 0 imaginary. We need a total of 4. I keep saying imaginary. We have 0 negative. We need a total of 4, so we have 2 imaginary. The last possibility is that we have 0 positive roots. We know we have 0 negative roots. We need to get to a total of 4, so that means that we must have a total of 4 imaginary roots. So our final answer here, our positive, we have 4, 2, or 0. For the negative, we just have 0. And then for the imaginary, we have 4, 2, or 0. So that's all I'm going to do with you today, because it's kind of a lot to take in, even though it's just using these kind of like sign changes. And like I said, kudos to Descartes for noticing this pattern. It really is all about picturing like a possible x to the 4th and just moving it around and seeing where those solutions end up. But the actual process of doing this I know can be a little confusing. So you have 5 homework problems that look like this. Make sure you're entering your answers positive, colon, your numbers, comma, negative, colon, your numbers, comma, imaginary, colon, your numbers. It might be a little sensitive. It's not as sensitive to the spaces because it's a short answer response versus a numeric. But let me know if you're having trouble with it, and I can see if you're just wrong or if it's just how you're entering it. So I'll let you guys get to work. We have until 12:10, so stay on until 12:10. I'll tell you when you can go, and if you have any questions, let me know.